Okay, so in this last part of the tutorial, we're going to be looking at a different type of question. Till now, the questions we've been solving in this tutorial have been very procedure based. You look at the question, you write the data, you refer to the tables, and you solve them, right? There's not much thinking involved. However, now the questions are requiring thought to be completed. You have to think about what is going on, right? So, let us begin. The question says a sealed rigid vessel. Rigid means the capital V is constant, not zero. My bad. Is constant and it is equal to 1 meter cube and contains 2 kg water at 100 degrees Celsius. Now we are heating the vessel. If a safety pressure valve is installed, at what pressure should the valve be set to have a max temperature of 200 degrees Celsius? So what this question is trying to tell us is that we have to install a pressure valve such that the pressure valve will trigger when the T reaches 200 degrees Celsius. Right. So let's draw what is going on. This is a rigid vessel with capital V of 1 meter cube and 2 kg water at 100 degrees Celsius. And then it is still 1 meter cube because it is a rigid vessel, and we have 2 kg water at 100 degrees Celsius. Sorry, at 200 degrees Celsius because we are heating it. Right. So at state 1, if we calculate the specific volume, it is the total volume by the mass. So specific volume is 1 by 2 is 0.5 meter cube. Right. Now, if we see, this will remain constant because our capital V is also constant at 1 meter cube and our total mass of the substance, not in any state, is also constant at 2 kg. So at state 2 also, we will have a specific volume of 0.5 meter cube. Now, if we refer to the tables of water, just a second. We're not looking at the saturated water pressure entry because over here we have 200 degrees Celsius as the temperature, right? Okay, so if we look at table B.1.1 at 200 degrees Celsius, we have the Vf as 0.001156. Vf equals to 0.001156 and Vg equals to 0.12736 at 200 degrees Celsius. Right. So how do we determine the state of water at 200 degrees Celsius? This is our Vf. This is our Vg. Now our given specific volume is clearly more than Vg. So our given specific volume lies somewhere here, which means superheated. Therefore, at 200 degrees Celsius, water is superheated. Right. So now all we have to do is we have to find the pressure at which these two states will exist simultaneously, right? So if we refer to the superheated water table, and if we see our specific volume needs to be 0.5. So at 10 kilopascal, 200 degrees Celsius, it is 21 point something. Then it goes down to 4 point something at 50 kilopascals. Then it goes down to 2.4 something at 100 kilopascals. Remember, we are looking at everything at 200 kilopascals, at 200 degrees Celsius. So at 200 kilopascals, it goes down to 1.0 something. And if we keep saying like that, we see that at somewhere between 400 kilopascal and 500 kilopascal, we are getting the specific value of 0.5. However, at 400 kilopascals, the value is 0.53, and at 500 kilopascal, the value is 0.42. So that means our required pressure value will lie somewhere between 400 kilopascal and 500 kilopascal, right? Let's make a small table. At 400 kilopascals, our specific volume is 0.53422. At some pressure between these two, our specific volume is 0.5. And at 500 kilopascals, it goes below 0.5 at 0.42492. So, how do we find the unknown value of pressure? For this, we use linear interpolation. Basically, we use unitary method. What I like to do is imagine it as an equation of a line. Keep in mind that this is not the same PV graph that you are used to. This is something else entirely. So, at a pressure of 400 kilopascal, actually it will be the other way around. At a pressure of 400 kilopascal, our specific volume is 0.53422, and at a pressure of 500 kilopascals, our specific volume is 0.42492. If we join these points, and if we join these points, we can see that 0.5 lies somewhere here, and we have to find the corresponding pressure. So what can we do to solve this? First we can do is we can write down the equation of the line AB using two-point method. So y minus y1 equals to y2 minus y1 upon x2 minus x1 into x minus x1. Right. So on the y-axis we have the pressure values. So let us do that. Our load pressure is y1. Y, that is the pressure axis, minus 400 equals to y2, which is 500 minus 400 upon x2. x2 is the value corresponding to 500. 0.42492 minus x1, which is 0.53422 into x minus x1, and x1 was 0.53422. Now we have the value of the x-axis, right? Because we know at this point the value on x-axis is 0.5. So this is 0.5. So now the only unknown that remains in our equation is the y value. And since the y value is the pressure axis, we can say that this is the p value. So upon solving this equation, you will obtain the p value to be 431.308 kilopascal. Now a few clarifications regarding this question. To linearly interpolate, you do not have to follow this method necessarily. This is just how I like to do it. I like to draw a line and I like to see that everything is varying linearly. So all the corresponding points must be lying on the same line. So I write the equation of the line, I substitute all that I know, and I find the unknown. But if you know some other method of linear interpolation, you can use that as well. This is just how I like to do it, right? So with that, we have solved the question. What we did was that we found the state at 2 and it was superheated. And then we refer to the superheated table to find the pressure at which these two states will exist, so that when 200 degrees Celsius is reached, the pressure valve will blow. We found that required pressure is somewhere between 400 kilopascal and 500 kilopascal. And then we linearly interpolated to find that pressure is 431.3 kilopascals. Moving on to the next question. It says a 400 meter cube storage tank constructed to hold liquefied LNG assumed to be pure methane is also given here. If the tank contains 90% liquid and 10% vapor, by volume at 100 kilopascal, what is the mass of LNG in the tank? And what is the quality? Quality means quality factor into 100%. So we have to find X and we have to find mass. So let us just draw the diagram to get some clarity on what is going on. So we have CH4 here, and this is 400 meter cube. This is 90% liquid and 10% vapor at 100 kilopascals. So this is liquid, this is vapor. 90% liquid by volume, which implies 90% of 400 meter cube equals to volume of liquid, Vf. This is capital V, this is not small v. Why is this not small v? It's because we are we don't know the mass of the mixture yet, which is what we have to find, right? Sorry. So that means capital Vf equals to 360 meter cube or 90% of 400 meter cube, and capital Vg, that is the mass, that is the volume of the vapor, is remaining 10%, which is 40 meter cube or 10% of 400 meter cube. Now, if we see vapor plus liquid, both are existing. So, where is our substance on the TV graph? If you remember, this line is the only part where both the vapor and the liquid exist. So we can see that it must have something to do with the Vf and the Vg, right? And clearly, this is a saturated mixture, right? Because both of them are existing. So let us try to find the Vf and Vg values from the table. I think methane was in the end. Guys, please don't use a PDF. I'm begging you. The physical thermotable is so much better. I have to use PDF here because obviously I can't show you the physical thermotable on the screen recording. Where is it? Where is it? Get the thermotables printed, please. I think it's around here. Right, methane. Now we are going to look at saturated methane table at table B.7.1. Why saturated methane? Because our substance is in a saturated mixture, right? So our saturated methane table does not have the exact value of pressure at 100 kilopascals. it has the Vf and Vg values at 101.3 kilopascals, which I think is the atmospheric pressure. Yeah. But you can choose to interpolate between the 88.2 kilopascal and the 101.3 kilopascal. But since 101.3 is so very close to 100 kilopascals, we are just going to use the Vf and the Vg values. So let us write that down. Vf of, sorry, of saturated mixture at 100 kilopascals of methane, remember we are looking at methane table, is equals to 0.002367. Vg, now these are the small v values because in the table we are giving the specific values, equals to 0.55665 meter cube per kg, meter cube per kg. And over here I'm going to write meter cube. Okay, meter cube is written because these are not specific. Now we are going to use the definition of specific volume. Specific volume was given by total volume upon mass, which means the specific volume of the liquid is given by the total volume of the liquid by mass of the liquid. The real interesting trick here is to use this formula as 2, and we can also say specific volume of gas is the total volume of gas by the mass of the gas, right? Now, the mass of the liquid can be given by total volume of the liquid and the and divided by the specific volume of the liquid. Similarly, the mass of the gas can be given by the total volume of the gas upon the specific volume of the gas. So now we can substitute the values and we will see mf equals to vf, which was 360, upon the small vf, which was the 0.002367, and similarly mg, which was 40, upon the small vg, which was 0.55665. So mf will come out to be 16,890.2831 kilogram and mg will come out to be 71.8584 kilogram. So our total mass will come out to be 1690.62.1415 kilograms. So now we have to calculate quality, which means we have to calculate the dryness fraction. Now there are two ways to do this. We can use our equation of small v equals to Vf plus x into Vfg, or we can use the definition x equals to mass of vapor by total mass. Right. So I will be using this method simply because it is more convenient, because we have all of the quantities, right? X equals to mass of vapor, which we found to be 71.8584, upon the total mass, which we found to be 1690.62.1415, and X will come out to be 4.2025. X will come out to be 4.2504 into 10 to power minus 4 into 100%. And if we were to use this method, then our small v would be the total volume of the mixture 400 upon the total mass, which was 1690.62.1415, and Vfg value we would have gotten from the table using the 101 kilopascal as 0.54760, as, come on, 0.54760, and Vf value we already had over here, and we would have substituted all of these into here, and our x would have come the same as this. So that is how we solve this question. And intuitively also a low value of x makes sense because simply it is the percentage of vapor by mass. And since we saw that our mass of the liquid was so much, it should make sense that the mass of vapor should be less. So it makes sense that our x value will be very small. Now, moving on to the next question. This question. Let us read this question. Helium in a steel tank is at 250 kilopascals, 300 Kelvin, with zero point 0.1 meter cube. Then a, it is used to fill a balloon. The final pressure is 150 kilopascal. The temperature still is at 300 Kelvin. And now we have to find the volume of the balloon. So let us quickly draw out the situation just to get an idea of what is going on. This is our helium at state 1. P1 is 250 kilopascal. T1 is 300 Kelvin. And V1 is 0 0.1 meter cube. Then it is used to fill a balloon. Just a second. Our P2 is 150 kilopascals, which makes sense because some of the air from the tank has gone to the balloon. So the tank itself will not have that much of a higher pressure. T2 is 300 kilopascal, 300 Kelvin, my bad. And V2 is 0 0.1 plus some unknown term, let us call it V3, where V3 is the volume of the balloon because some air has gone into the balloon. Now we have to find V3. A simple way of doing this is to use PV equals to mRT and simply conserving the mass. Because if you look at it, this is a closed system. There is no interchange of air anywhere except inside the system itself. So we can say that PV by T equals to M into R equals to constant. Because mass is conserved in the system and R for helium is always the same no matter what. It is a constant value. So we can say P1V1 by T1 equals to P2V2 by T2. Upon solving this, our V3 is 0 0.1, our V2 is 0 0.1 plus V3. So upon putting this value and all of the others into this equation, V3 should come out to be 0.0667 meter cube, which is 1 by 15. Right. This was a simple question. Moving on to our last question for this tutorial. Okay, this is a bit of a tricky one, so we'll have to do it very, very carefully. In fact, this entire tutorial is a bit tricky, requires a lot of thinking. Right, let's read it. 1 meter cube rigid tank has propane at 125 kilopascal 300 Kelvin. Propane at 125 kilopascals 300 Kelvin and connected by a valve to another tank of 0.5 meter cube with propane at 250 kilopascals 400 Kelvin and a volume of 0.5 meter cube. Then this valve is opened and they go to a third state with some pressure P3, which is given, which is not given to us, which we have to find. The final temperature at 325 Kelvin, and the final volume will obviously be the volume of A plus B, because now they are connected, they behave as one single tank, and equals to 1.5 meter cube. So again we do the same thing as above, just slightly more complicated. Again we use mass conservation, because see, this system again is closed. There is no exchange of mass except inside the system itself. So the mass in the tanks initially has to be the mass in the tanks afterwards, right? So PV equals to MRT. The mass in tank 1 initially was 125 into 1 by 300. The mass in tank 2 was 250 into 0.5 by 400, and then the final mass is added up because the valve is opened, and at the mass at state 3 will become the pressure P3 into 1.5 upon the equilibrium temperature, which was 325 Kelvin. So we can say 125 into 1 by 300 plus 250 into 0.5 by 400 equals to P3 into 1.5 by 325. So upon solving this, our P3 will come out to be 157.98 kilopascal, which is approximately 158 kilopascal. So this question, basically we conserve mass. You just have to be smart enough to realize that there is no mass exchange taking place except inside the system. In this question we also did the same thing, except you have to keep in mind that 0.1 plus V3 is the important statement here. Obviously we can solve it using some other variable and then subtract 0.1 from that, but I find it better to keep in mind initially that the volume has gone somewhere else into the balloon. In this question, we have to keep in mind that the gas is on this line, which is why we are able to use the values of Vf and Vg. And these two formulas are perhaps one of the most useful tricks in all of the thermodynamics, because everybody knows how to use this, but nobody actually knows how to split it into Vf and into Vg. Nobody is able to think of this, that ye bhi ho sakta hai, So this trick is very useful. And in the above-most question, we learned how I'll do linear interpolation and how to use the superheated table when our exact data is not given. If you know some other method to do linear interpolation, feel free to do so. Right. With that, this concludes our chapter of pure substances. And after this, we'll be moving into heat and work.